make a video of this little section on a couple of points from the titration questions that you've just been looking at, and then I'm going to teach you how to do back titrations. So the first thing, just to remind you, if you're looking at this video, to do the in thinking homework, the one that I've just set you, and then we're going to just look at question 8 from the pack together. It tells you in the question that there's a sample of 250 centimeters cubed of sodium hydroxide made, and that they did a titration using 25 centimeters cubed of that. 25 of that was put into a conical flask, and a titration was done, and you do the titration calculation exactly like we've always done them, and you should end up working out the number of moles of HCl. So I'm just going to miss out all the grid stuff, and I'm just going to get Nia to tell me the answer here. So the number of moles of HCl you get from doing 28.2 centimeters cubed times the concentration divided by 1,000. And what did you get for that, please, Nia? 2.82 times 10 to the minus 3 moles. That was the moles of HCl. This was a reaction between HCl and NaOH, so we can say the number of moles of NaOH was the same as that in 25 centimeters cubed, right? Now, it might be you've gone ahead and worked out the concentration of the sodium hydroxide there, but it doesn't ask you. For that. I'm just going to get rid of that so you can see a bit better. Right, so that's the number of moles of sodium hydroxide in 25 centimeters cubed. Right, so that's what we used. But it asks you how many there were in 250 centimeters cubed. The number of moles in 250 centimeters cubed is that number times 2, which is 2.82 times 10. Sorry, number of moles in 250 centimeters cubed is 10 times the number of moles in there, obviously. So it's 2.82 times 10 to the 2 moles in 250 centimeters cubed, right? And it asks you what mass of sodium hydroxide is required. So there's nowhere in there you need to work out the concentration. You can work out the mass of sodium hydroxide in grams, because mass is equal to mR times the number of moles. So it's 2.82 times 10 to the minus 2 times by the formula mass of sodium hydroxide, which is 40. 40 times 2.82 times 10 to the minus 2, Nia, is a bit louder. 0.183 grams. Does that match the answer in the back? Should do. Yeah, we just realised a bit of a typo there in a calculator, so it's 1.13 grams, and that's how you do questions like that. You see how they're a little bit harder than GCSE, but you'll complete those questions on top of the work that I've already set you to do, because you need to practice these things. I'm now going to talk you through how to do something called back titrations. Now, there's lots of information in the pack, but I'd really like you to listen. You don't need to write anything down right now. Listen and concentrate. When I'm talking you through something that's quite difficult and you're fiddling around and copying and writing, you're not processing what I'm saying. So please carefully listen in. I'm going to put this video on the Google Classroom. If you want to watch it again, you can do. You want to write it up, you can do. Alright, so forget all that. A blank bit of paper would be really helpful if anyone's got any, because I'm running out here. Thank you so much, Carl. Right, so a back titration is something that comes up now and again in IB, and it will also potentially come up in your coursework, where I'm going to give you an example of one without any numbers to start with, and then we're going to use one of their examples. It's important. It's one of these ones that the numbers, coming up with the numbers on the fly, doesn't work so well. So an example of an IA we've done before, and I'll never let anyone do this again because it's a horrible IA. Someone wanted to work out how much calcium carbonate there was in some eggshell. It's basically all calcium carbonate, which is why it's pretty boring IA coursework. But so what you do, you'd want to say, oh well, I know calcium carbonate reacts with hydrochloric acid to give you, you know this in year 9, right? Calcium chloride, carbon dioxide, and water. So, well, I'll just do a titration, right? I can do the acid, find out how much acid is required until all the calcium carbonate's used up. But it doesn't work. It doesn't work as a titration because the calcium carbonate is a solid, and this reaction is much slower than the instant neutralizations we do in solution that we normally do, right? So we have to do this quite a different way. So what we do, instead of doing a titration, when we've got a solid, instead of doing a titration, what we do is we react all of the calcium carbonate that we've got, all of the eggshells that we've got, but we make sure that we've got an excess of the acid. To do that, you kind of make a rough idea. Let's say I've got a gram of let's say I've got a gram of eggshells. Well, I can work out roughly how much calcium carbonate is going to be in there by doing a little bit of maths. Okay, well, let's do that, shall we? So let's say we've got a gram of eggshells. The formula mass of calcium carbonate is 100. So moles equals mass divided by the MR. 1 divided by 100 is 0.01 moles. So I need to make sure that the maximum number of moles I've got is 0.01 moles of calcium carbonate. It's the maximum I've got. But I know eggshells are impure, so it's going to be something less than 0.01. So what I'm going to do is I'm going to add an excess of the acid. But the important thing here, you realise, that it's a known value. So instead of adding 0.01, in fact I am going to add exactly 0.01 moles of sodium hydroxide, sorry, what do you call this stuff? Hydrochloric acid to it. So I've got 0.01 moles of hydrochloric acid adding to my calcium carbonate. I know, because the eggshells aren't pure, that all of the calcium carbonate in the eggshells will have reacted. But that's going to leave me with an excess. It's going to leave me with some left over, right? So I've got eggshell, pour some acid in. I know I've got more acid than calcium carbonate, so I must have a little bit of acid left over, right? Make sense? Happy so far? Nod if that's makes sense to you. Some people are nodding even though they're going nodding with a confused look, which is quite entertaining. But when you see a few examples, we'll get the hang of this. Right, so the way to find out how much excess acid we've got is by doing a titration. Yellow.
If there was the maximum for calcium carbonate is 0.01 mole, wouldn't you have to use 0.02 moles?
We can use 0.02. I'm saying I know this can't be more than 100% pure calcium carbonate. It's going to be less. So that's the maximum it could possibly be. It's more likely to be 95%. So
if this is a 2-to-1 ratio, wouldn't you have
look at you, clever clogs. Yeah, well done. Thank you for that. Well done. It's a 2-to-1 ratio. That's why we always put the ratio at the stop. Well spotted. 10 points to Gryffindor. Yeah.
And when you sums up like 2 to another 0.02 is going to be just 0.2, just got
That's
the maths.
it. Okay, so we're going to use at least 0.02 moles of HCl. We've got a known concentration and we add a known volume, maybe using a burette or using a pipette or whatever. So then you do a titration of the HCl with sodium hydroxide or some other alkali, and they react in a 1-to-1 ratio to give you, as we did before, sodium chloride and water. And we do a titration, we use volume, concentration, number of moles, and we find out how much sodium hydroxide was required. So let's say there was only a tiddly little bit of sodium hydroxide. Let's say it's 2 centimeters cubed, and the concentration is 0.1 mole per litre. We can work out the number of moles of sodium hydroxide there. So 2 times 0.1, that comes to 2 times 10 to the minus 4 moles of sodium hydroxide, right, were required to neutralise the HCl that was left over. So that's that value there, 2 times 10 to the minus 4. Nod if I've got the maths right. Are we happy? Gabriel? Happy? Good, getting it right this time. So we don't need to work out the concentration, that's irrelevant. We're just working out how much excess there was. So we started, this is the trick, this is the whole key to back titrations. The key is that to work out the number of moles of excess HCl, what we do is we know how much we started with, 0.02, and we used up all of it except 2.0 whatever it is times 10 to the minus 4. I've screwed that one. Yeah, that's right. That's what's left over. That is right. And that, please, I can't do. So it's 0.01998.
It's 0.0198.
Yeah, that looks right. Okay. Moles. So that's how many moles of so 0.2 is the number of moles of HCl we started with. 0.002 whatever it is the amount of HCl was left over at the end. So the amount of moles of HCl used up, that's what I did wrong there. So the number of moles of HCl that were used up in the reaction must have been 0.0198. The number of moles HCl used up is equal to 0.0198, and that was in this reaction between calcium carbonate and HCl. So 0.0198 were used up. We divide that by 2 to work out how many moles of calcium carbonate there must have been then. So we divide that number by 2, please. Moles of calcium carbonate, and we can work out the mass of calcium carbonate. That would be equal to, so the mass is equal to the number of moles times the MR, so we do that number times 100, which is 0.99 grams of calcium carbonate in our 1 gram sample, right? So it's 99% pure, which is basically what happens in real life. Okay, so that's the overall process. Now, rather than, that was me hopefully just talking you through in general terms, I'm now going to get you to, we're going to work through one from the textbook together. I'm going to show you there's another worked example here. So there's literally no point you sitting writing out the one that we've just done. We're going to, there's one here worked out for you, and we're going to work through this one together. Okay, so aspirin is a monoprotic acid, HA. They can be analysed with a back titration. They use 0.25 moles of sodium hydroxide, the excess, to however many moles of aspirin that we don't know how many there were, and we ended up with a stock solution. This is getting a layer more complicated than the first one because we've got to use we're using a stock solution. We titrate 25% portions, each of which require 0.01 moles of HCl for neutralization. Right, so we're going to work through this bit by bit. So we always start with the titration. We start from the end. We start from the last reaction that happens. Always, always, always. The number of moles of HCl is equal to 0.01, and that's the number of moles of HCl in the neutralization, the titration. Okay. The solution we're titrating against is the excess sodium hydroxide, the excess, the stuff we left over from the titration. Okay, so the number of moles of excess NaOH, therefore, because it's a 1-to-1 ratio, must also have been 0.01. We've worked out from the titration. We're happy so far. Nod if that makes sense. Or don't nod. Nod? Does that make sense? Number of moles in the titration was that and that, because they're 1-to-1 ratio. Yes or no? Okay, so that came from, this is where it gets slightly difficult, that was in 25 centimeters cubed. So the number of moles of excess NaOH is equal to 0.10 in 250 centimeters cubed. Okay, that's how many moles of sodium hydroxide were left over, were excess in that when it reacted with that after it reacted with the aspirin. Okay, we started with the number of moles of NaOH initially was 0.25. And so to work out how many moles of the NaOH that we used up, we do 0.25, which is what we started with, take away the amount that there was in excess, in 0.10, that leaves us with 0.15 moles of sodium hydroxide that we used up in that chemical reaction, okay, between the sodium hydroxide and aspirin. And given that aspirin is a monoprotic acid and sodium hydroxide is monobasic, the number of moles of aspirin must be the same as the number of moles of sodium hydroxide that we used up. Aspirin. It's also equal to 0.15. Okay? We're asked to work out the number of moles of aspirin, and so that's what we've done. Sometimes you have to work out the mass. Now, I fully accept that that is blooming difficult and takes a bit of practice, and will take you some practice, which is what you're going to spend the next 14 minutes doing. I'm going to work quietly through, silently through the next example if you want to do that with me, or you can just crack on and try the 5 questions over the page. But I recommend, actually what you should do first of all is do this one. You can just look up to see where you've gone wrong, if you've gone wrong. I'll keep taking the video so you can refer back to it if you want to as well. So we're just going to work silently from this point. Okay. That's right. Probably check in the back those 2 example questions to be done correctly. It would be helpful if someone could just check the answers in the back for me so I can leave this here.